Because the traveling salesman problem is famously hard to solve as the number of cities increases, heuristic methods come in handy. So let's start with a quick definition. A heuristic is a kind of shortcut, a method designed to get a good enough solution faster, even if it means sacrificing accuracy or completeness. In real-world applications, time and resources are limited, so these trade-offs are often necessary. In the context of the TSP, three popular heuristic algorithms are the nearest neighbor, the greedy algorithm, and simulated annealing. Let's take a closer look at each one. The nearest neighbor algorithm is probably the simplest to understand. You start from a random city and repeatedly go to the closest unvisited city until all of them are visited, and you can return to the starting point. This method is fast, its time complexity is n squared, but it's not always accurate. In fact, as the number of cities increases, the quality of the solution often gets worse. That said, it still performs reasonably well for small or moderate-sized problems. For example, when it was tested on problems from the TSLIB library, which is a standard set of TSP instances, the nearest neighbor algorithm typically gives solutions about 1.26 times longer than the optimal route. So it's not perfect, but it's definitely useful in practice. Before diving into the next algorithm, let's clarify a few terms just so we're all on the same page. A node is just a city or a point in the graph. You might also hear it called a vertex. An edge connects two nodes and has a cost or weight like a distance. A cycle is a closed path that starts and ends at the same node without repeating any in between. Now let's talk about the greedy algorithm. The basic idea here is to sort all the edges by cost and add the shortest ones to the tour, as long as doing so doesn't create a smaller cycle or make any node have more than two edges. You keep doing this until you've added exactly n edges. This approach tends to produce better solutions than nearest neighbor. However, it's also a bit slower, running in about n squared log n time. That extra cost in computation might matter depending on the application. Finally, we have simulated annealing, which is a more advanced and adaptive method. The name comes from metallurgy, where annealing involves heating a material and then slowly cooling it to remove defects. The idea in computing is similar. Start with a high degree of randomness, call it the temperature, and gradually reduce it to refine the solution. Here's how it works step by step. First, you generate an initial solution, often using something like the greedy algorithm. Then you repeatedly modify the solution by changing a segment of the path. You either reverse it or move it elsewhere. After each change, you compare the new path length to the original. If the change improves the route, you always accept it. If it doesn't, you might still accept it based on a probability that depends on the algorithm's current temperature, which is the value that decreases over time. This randomness helps escape local optima. Eventually, when the system cools down and there are no more useful changes, the algorithm stops. This process is flexible and can be tuned by parameters like the initial temperature value, the cooling rate, and what you choose to be the stopping condition. You might run 100 times n changes, or stop after a set number of improvements, or a lack thereof. Simulated annealing balances exploration and refinement. It's slower than the earlier heuristics, but often gives better results. And just like physical annealing, the gradual cooling makes it more likely to settle into a good, stable solution. So to wrap up this section, the nearest neighbor is simple and fast, but it's not super accurate. The greedy algorithm is slightly slower, but tends to give better results. Finally, simulated annealing is more complex, but offers the best quality among the three, especially for larger problems. Each of these heuristics has a place, depending on how much time and accuracy your situation demands. So now that we've looked at heuristic methods which give us fast approximate solutions, let's talk about exact algorithms. Unlike heuristics, exact algorithms are guaranteed to find the optimal solution. But of course there's a catch. They're usually only practical for smaller problem sizes. The reason is computational complexity. These methods can grow exponentially with the number of cities, so they're often limited to around 40 or 60 nodes in practice. Despite that, they're incredibly important, especially for benchmarking how close other methods come to the true best solution. Most exact algorithms begin with a good enough tour, often found using heuristics, to establish an upper bound. From there they work to either prove that no better solution exists, or refine the current one until optimality is reached. Let's go over two major exact approaches, the Bellman-Heldkarp algorithm and branch and bound. Dynamic programming is a programming technique that solves problems by breaking them into overlapping subproblems and storing the results to avoid redundant calculations. This concept is at the heart of the Bellman-Held-Karp algorithm. Here's a simple example. Imagine a TSP with just 3 cities. Call them X, Y, and Z, with X as the starting point. You could go from X to Y to Z to X, or from X to Z to Y to X, and both are valid, but some of the cost calculations, like the distance from Y to Z, are used in both paths. Instead of recalculating those, dynamic programming stores and reuses them. The Bellman-Held-Karp algorithm uses this idea to systematically build up the best path by considering all subsets of cities. It stores the shortest path to every subset, ending at every possible city. Here's how it works in steps. First, you number the cities from 0 to n-1. Then you define a function, CSJ, to represent the cost of the shortest path starting at city 0, visiting all cities in subset S, and ending at city J. The recursive formula is on the slide, with the base case as well. Finally, to complete the cycle, we return to the origin. This algorithm has a time complexity of n squared times 2 to the n, which is a huge improvement over brute force's factorial time, but still only scalable up to about 40 to 60 cities. Next is branch and bound. This one takes a totally different approach. It uses a decision tree of possible paths and intelligently prunes branches that won't lead to a better solution. The basic idea is to estimate a lower bound on the cost of completing a partial tour. If that estimate is already worse than the best full tour we've found, we don't bother exploring that path. One common way to compute a lower bound is using a minimum spanning tree of the remaining cities. This gives a quick estimate of the cheapest way to finish the route. We also factor in the cost to return to the starting city. Each time a new city is added to the tour, we create a new branch, but before diving deeper into that branch, we compute the lower bound. If it's not promising, we cut it off. That's the bound part of the algorithm. This method is highly dependent on how good your lower bounds are. Strong, tight bounds mean less time wasted exploring bad paths. Weak bounds mean you might explore way too many options. In practice, heuristics are often used to guide branching and tighten bounds, so there's a nice interplay here between exact and heuristic methods. So how do these two methods stack up? Bellman-Held-Karp systematically explores all subsets, reusing calculations through dynamic programming. Branch and bound tries to be smarter by exploring only the most promising branches using bounds. Both methods are much more efficient than brute force, but they still face exponential time growth, especially as the number of cities increases. That's why in real-world scenarios, like routing trucks or drones, companies often rely on fast approximations or hybrid models. But even then, exact methods are still the gold standard for comparison, and for cases where near optimal isn't good enough. To wrap up, exact algorithms show us how far we've come in terms of solving the TSP efficiently. They demonstrate the power of smart recursion, dynamic programming, and smart pruning. But they also show us the limits of what's possible when inputs get large. That's where approximation algorithms like Christophanides come into play. They guarantee a solution that's within a certain factor of the optimal, and we'll be looking at that next. When dealing with a problem as famously difficult to optimize as the TSP, approximation algorithms become especially valuable. These methods aim to strike a balance between speed and solution quality, and unlike heuristics, which rely on empirical performance, approximation algorithms come with mathematical guarantees about how close their solutions are to optimal. The best known and most celebrated approximation for the TSP is the Christophanides-Sergikov algorithm, which guarantees a solution that is no worse than 1.5 times the optimal tour. A slightly better algorithm was introduced in 2020 by Carlin, Klein, and Garan, but its improvement is very small. For the purpose of this presentation, Christophanides-Sergikov will remain the focus of this section. Before we get into the steps of the algorithm, let's define a few important concepts it relies on. First, a minimum spanning tree, abbreviated MST. This is a set of edges that connects all vertices in the graph with the minimum possible total weight and with no cycles. Algorithms like prims build an MST greedily, always adding the smallest edge that connects a new node to the growing tree. A Eulerian tour. This is a path that visits every edge exactly once and returns to the starting point. It's only possible if all vertices have an even degree. Next, in a graph with an even number of vertices, a perfect matching pairs up all vertices using edges that don't share endpoints, and the goal is to do this with the lowest possible total weight, hence perfect. Now for Christophilidis-Serdyukov to work, the graph must be symmetric, meaning the distance from point A to B is the same as from B to A, and it must obey the triangle inequality, which says that the direct path between any 2 points is always the shortest. This property is what allows the algorithm to shortcut certain steps later without increasing the total cost. Let's go through the steps. First, you build a minimum spanning tree of the graph, which connects all points with the lowest possible total cost. Second, identify the vertices with odd degree in the MST. These are the ones that prevent us from building an Eulerian tour. The next step is to find a minimum weight perfect matching between those odd degree vertices. This is the most computationally expensive step, and it defines the algorithm's time complexity as n cubed. Next, you combine the matching with the MST to form a multigraph, where all vertices have an even degree. This guarantees the existence of an Eulerian tour. Lastly, you create the Eulerian tour, and then shortcut any repeated vertices to create a Hamiltonian tour. The triangle inequality ensures that shortcutting doesn't increase the cost. Now let's look briefly at why the algorithm guarantees that its result is no worse than 1.5 times the optimal. Let OPT be the cost of the optimal TSP tour, let T be the cost of the MST, let M be the cost of the minimum perfect matching, and let C be the total cost of the Christophilidis tour. Also let O be the set of odd degree vertices in T. Here's the logic. Every TSP tour contains a spanning tree, so the MST has a cost less than or equal to OPT. Second, the number of odd degree vertices in any graph is even, so a perfect matching exists. Using the triangle inequality, we can show that the cost of the minimum weight perfect matching on the odd degree vertices in T is smaller than or equal to half the cost of the optimal TSP tour. So when we combine the minimum spanning tree and the minimum perfect matching and shortcut repeated vertices in the Eulerian tour to form a Hamiltonian tour, the triangle inequality ensures the total length does not increase. Therefore, the cost of C is smaller than or equal to the cost of T plus the cost of M. From the above proof, we have the final formula proving the 1.5 ratio. To summarize, approximation algorithms like Christophilidis-Serdyukov offer a powerful middle ground between speed and precision. Unlike heuristics, they offer provable bounds on how far their solutions can be from the best. Christophilidis is elegant in its use of classical structures, minimum spanning trees, perfect matching, and Eulerian tours. In the world of optimization, especially for NP-hard problems like the TSP, good enough with a guarantee is often the best we can hope for.